I don't know about you, but I'm freaked out by the fact that microplastics are being found everywhere. Like, I don't know, in the brain, or like on top of the highest mountains and in the deepest trenches in the ocean. So when I say that Gen Z needs to make AI eat plastic, I'm not joking. We, as a human race, need to use AI to design things that are going to eat these microplastics and break them down into something that won't stick around inside our bodies forever. And I think that Gen Z has a chance to make the difference here. By the end of this video, you're going to have an exact framework of how scientists are eating plastic already, as well as how Gen Z can help save our planet using these technologies. Welcome to my journal club, where I read recently published papers that I find cool and put them into a broader context so that you can stay updated on the most cutting-edge research. In case you're interested, I'll be diving even deeper into these sources and showing the behind-the-scenes details of my research and my channel in my newsletter. Check the link in the description to sign up. So for this video, I found this paper that was literally published about 2 weeks ago at the time of writing this. Coming out of the University of Texas, the first 3 authors are Daniel Acosta, Daryl Barth, and Julie Bondi. These 3 were all graduate students, and if they aren't in Gen Z, then they're very close to it. And they actually come up a little later in this story as well. This shows how much of an impact that Gen Z is making already. They're discovering special microbes that eat plastic called PETases from deep sea floor samples that can break down the exact plastics that we are polluting our bodies with today. What they found might change everything. To hear just how they're doing this, stick around until the end of the video when I go over the paper in full detail. But first, I need to give you the context of the problem, describe what these PETases are, and outline how Gen Z are already using these tools to change the world. Okay, so basically, here's the problem. We have a ton of plastic pollution, but don't worry, we're making more and more plastic every year, and we're also barely recycling any of it. And almost all of the plastic that we make isn't regulated, and it's really hard to clean up because plastics are very hard to break apart on a chemical level. This is what makes them so incredibly useful. That's what makes them sterile materials that we can use in hospitals. That's what makes them so renewable, easy to use, right? Or that's what makes them so durable, easy to use. But it also makes them stick around for a long time. And when they do break apart, they don't really break into something different, but just into a smaller piece. And so they break into smaller and smaller pieces until they can get into your bloodstream and up into your vital organs. That's why we're seeing these microplastics in people's brains. So what if I told you that using recent technologies, including AI, we could figure out a way to eat these plastics and turn them back into being brand new and make a circular plastic economy? Or we could turn them into something totally different entirely. But first, I need to tell you something that most people don't know about plastic recycling. There are tons of different types of plastic, and they need different techniques to recycle them. This chart here shows the percentages of different plastic types. You don't need to memorize this, but just know that they all have different challenges. You definitely recognize these 3. Polyethylene. This is the most common type because it's very versatile. It can be low density like a crinkly grocery bag, or high density like a shampoo bottle. It's chemically simple, basically just a long chain of carbon atoms. Polypropylene. PP is super similar to PE, but it's like the heavy-duty version. It has an extra methyl group that acts like a shield, making it stiffer and, more importantly, heat-resistant. You'd recognize this as Tupperware, takeout containers, or pill bottles. Polyvinylchloride, PVC. This is the toxic, heavy-duty one. The chloride attached to the chain makes it incredibly hard and resistant to bacteria, which is why we use it in plumbing pipes and credit cards. I know what you're thinking looking at this chart. PE and PP take up way more of the pie. Why are the exciting papers that we're talking about today focusing on PETase, which is only 6% of the pie? To answer that question, we have to dive a bit deeper into the chemistry. By the way, if you want a cheat sheet of these plastic types and which ones are actually recyclable, I've got a free guide included in the newsletter for this video. Sign up below to grab it. The reason that we don't hear as much about recycling PE or PP is simple. It's a lot harder. Polyethylene and polypropylene have backbones made of carbons linked to other carbons. This bond is super strong. PET, on the other hand, has a weaker backbone with an ester bond, so it's easier to cut. But there are exciting things happening with these harder plastics. Recycling them wouldn't look like bottle to bottle. Instead, it involves breaking a Tupperware container into molecules that bacteria can eat. The bacteria then convert that plastic into a new type of biodegradable plastic called PHA, or even into fuel. There are companies like Genesis in Toronto doing this right now. For polypropylene, though, that extra methyl group acting like a shield makes it harder for enzymes to latch on. However, in 2025, there was a breakthrough showing how human digestive enzymes might actually be able to degrade polypropylene. These are super new fields, so the potential is wide open. But for now, let's look at the success story, PETase. So, why is PETase such a big deal? First, PET is what water bottles and polyester clothing are made out of. It's valuable because it can be clear, airtight, or even spun into fibers. This is why water bottles are so often turned into jackets or running shoes. The history here is crazy fast. Before 2016, we didn't really have anything efficient, though we did know about the existence of enzymes that might be able to eat PET. But in 2016, Japanese researchers discovered Ideonella sakaiensis in the mud. Discover Ideonella sakaiensis in the mud. Sakaiensis in the mud. Japanese researchers discover Ideonella sakaiensis in the mud outside a recycling plant. It could eat plastic, but it was slow. In 2018, researchers accidentally engineered a form of PETase which was 20% faster. But in 2022, there was this AI boom in protein engineering. A team at UT Austin used machine learning to scan thousands of mutations at once. They created a variant that could break down entire containers in just 24 hours at 50 degrees Celsius. Now, there are companies like Carbios in France and Samsara Eco in Australia that are building massive plants to do this at scale with big companies like Nestle, L'Oreal, and Lululemon. This brings us to the paper that dropped just 2 weeks ago. This team, which happened to have some of the same researchers and came out of the same school as this machine learning paper that I just talked about that found the really fast PETase, this team decided that instead of looking on land, they're going to look somewhere extreme, a deep-sea hydrothermal vent system in the Gulf of California. Why there? Because they wanted enzymes that could survive high heat. If you want to recycle plastic faster, you need higher heat, but heat usually destroys enzymes. They needed one that was born in the fire. They used a technique called metagenomics, which I think is super cool. They took a sample of the hydrothermal vent and they sequenced the DNA of all the things in that sample at the same time. Essentially, they extracted all the DNA by using chemicals to split open the cells and then purification steps with special filters and centrifuges. They then chopped the DNA into little pieces and sequenced all of the pieces at the same time. They used some crazy computer math wizardry to figure out which pieces went together, and they were able to look at all of the genes that were present in the DNA of the sample that they picked up from the bottom of the ocean. That's insane that they can do that. Anyway, this gave them this crazy data set with all the different DNA from their sample. And they used a hidden Markov model, which is basically a complex AI word search that looked at their DNA data and it compared it to the DNA data of plastic-eating enzymes to see if there's anything that looks kind of similar. Basically, it's a word search with a list of words that it's looking for, and it's looking at the puzzle and it says, okay, are there any words that are spelled kind of similar? They did find 22 candidates that stood out, but one of them really was the star of the show, GuaPA. So there are a couple reasons why this one is kind of the standout. of all of the standouts. It's an archaeal enzyme. This is the first time that we've seen an enzyme from the archaea domain that can degrade PET films. This is a huge deal because every other PETase that we found before have come from bacteria, which is a totally different branch of life. GuaPA is also super stable because it evolved in a vent. It can survive the industrial heating processes that would be needed to break down plastics. But I'm only telling half the story. There's another factor here. They also discovered 2 new enzymes that eat the intermediate products and help GuaPA digest the PET even faster. When they combine GuaPA with these new enzymes, these BHETases, there was a massive boost in efficiency. These BHETases eat the intermediate products and convert it into the final product from PETase. This shows a principle of a consortium theory. It's not likely a solo act to break apart these PET plastics, but rather a team sport where one enzyme shreds through the tough PET and other neighbors, these BHETases, clean up the scraps. This is the perfect analogy to pivot to why I think Gen Z is in the perfect position to change the world with this plastic-eating technology. Here's why this is our moment, and the responsibility falls squarely on our shoulders. We aren't kids anymore. We're moving into the real world, and this is where we can have a real impact. But for us, we have an insane amount of tools at our disposal, and we are more uniquely positioned to change the world than any other generation before us. When it comes to solving our plastic problems, the code has been broken. We know that nature can evolve to break down these synthetic materials, and we know that we can guide that evolution with new technologies. Instead of shredding bottles into a low-quality carpet, we could take these bottles, dissolve them into their base components, and rebuild them into brand new bottles, and make a circular system of plastic usage. The only thing missing is the ability to do this with scale and with other types of plastic. This is where Gen Z comes in. This is our fight, and we were born into it using the tools that we'll need to fight it. These advances in technology that used to be happening in a lab with pipettes are more frequently happening in computers using AI models. We're digital natives, having grown up with this technology our entire lives. We have a unique chance to adopt these tools and use them to create the future that we want to see. There are certainly going to be major challenges. PET might be an easy mode plastic, and the hard mode plastics are going to be harder to break down. However, the recent developments in these fields are giving us an opportunity to expand on these findings and accelerate the enzymes the same way that we have with PETases. We have an opportunity to use these new technologies for good, to kill the concept of waste entirely. We could make a future where plastic becomes a circular system, and we can ensure our nature and bodies are free from potentially harmful microplastics. This industry is at a tipping point. There are pilot plants, proof of concept, but it has yet to become truly scaled and have mass adoption. If our generation pushes it by becoming the people who build this future through engineering, policy, and business, we can make it the standard. We know how to do it. We just need to build it. If you want to join a community of people who are actually optimistic about the future of science, you need to be on my newsletter. I'm going to be talking about these exact type of topics, framing the scientific field in a positive light and demonstrating the ways that we can build positive solutions. I'm also going to be looking at the specific companies that are working in these fields and talk about the sources that I used for this video. Thanks for watching.